Welcome to JCE Connect. In this video, we will be discussing about the design of a staircase. So staircase is a structural element which provides us a mean of communication between different levels of a building. So these are the parts of a staircase. This is called the waist slab. This part is called the landing slab. This is the foundation of a staircase. The vertical members are called risers and the horizontal members where we keep a foot are called treads. So usually tread is provided as 300 mm for public buildings and lesser for residential buildings. So similarly, for public buildings the rise is kept smaller than the residential buildings. So to calculate the effective span of a staircase, we refer to the clause number 33.1 of IS 456/2000. So as we can see in the figure, the length of the effective span varies depending upon the position of the mid-landing beams. So these are the mid-landing beams. So with respect to the position of the mid-landing beams, the effective length changes. As we can see in the figure number 1, the effective length is smaller and it increases in the second figure as the mid-landing beams are in between the landing, and it is higher in the third figure because the mid-landing beams are at the end of the landing portion. So let us see a problem for a dog-leg staircase for the following details. The staircase room is given, the size of the staircase room is 2.1 meter and the length is given as 4.48. The floor to floor height is given as 3.2 meters. This is the floor to floor height, and the width of the wall, that is the bearing, that is 250 mm. The live load to be considered is 3.3 kilonewton per meter square and the floor finish is 1 kilonewton per meter square, and we use M20 concrete and Fe415 steel. So part 1 is fixing up of the dimensions. We assume a rise of 150 mm and a tread of 250 mm. So assuming a clearance of 0.1 mm between the two flights, so this is the flight and we travel in this manner. So this is the clearance that we provide of 0.1 mm. So coming to the calculation, width of the flight is calculated as 2.1 minus 0.1 by 2, that is this width minus the clearance divided by 2, that is 1 meter. So each flight is of 1 meter width. The height to be covered by each flight is 3.2 meter by 2, that is equal to 1.6 meter. So this height is totally 3.2. The height to be covered by each flight is half of 3.2. Okay. The number of rises is equal to height divided by rise. So the height to be covered by each flight is 1.6 meter, that is 1600 mm divided by 150. 150 is the assumed rise. So we get 10.66. So let us take 10 number of risers in each flight. So actual number of risers will be 1600 mm divided by 10, that is this. So we get 160 mm as the actual height of risers, and we had assumed a rise of 150 mm, so the actual height is 160 mm. The number of treads in each flight is equals to number of risers minus 1, that is 10 minus 1 is equals to 9. The total space occupied by treads is equal to 9 into 250 mm. 250 mm is the width of the tread. So 9 number into 250 gives us 2250 mm. So the space available for landing will be total length, that is 4.48 meters minus this total space occupied by the treads, and we have to divide this space into two landings. So we get 1115 mm as the space available for landing. So thus we provide in each flight 10 number of risers and 9 number of treads, and the mid landing of width 1.115 meter. Coming to part 2, the first step is to design the first flight. The step 1 consists of fixing up of the dimensions. We know the effective length formula is equals to 9 into 250. These are the number of treads. This is the width of each tread. This is the mid landing width, and this is the bearing. So we take half of the supporting wall length. So this way we calculate effective length. That comes to 3.49 meters. The depth of the waist slab, the effective depth is calculated by this formula, span by 20 into modification factor. Similarly, the modification factor is calculated similar as that of slab. So 3.49 is this into 20, and we assume 1.3. So we get an effective depth of 135 mm. Assuming a cover that is d dash of 15 mm and 10 mm dia bars, we calculate the total depth of the waist slab, that is d plus d dash plus 5 by 2, that is we get 155 mm. Coming to step 2, that is load calculations. First step is to calculate the load due to self weight of the waist slab. Consider B to C as the waist slab. So the formula to calculate that is W dash into R root of R square plus T square whole divided by T, where W dash is equals to depth of the waist slab BC into density of concrete into 1, that is the width of the slab. So depth of the slab, as we have calculated in the previous step, is 0.155 meter into density of concrete is 25 into 1. We get 3.875 kilonewton per meter. Therefore, the load is equals to 3.875 into 0.16, that is the rise, plus 0.25, that is the tread, divided by 0.25, that is the tread. We get 4.6 kilonewton per meter. This is the load due to self weight of the waist slab. In the second step, we have to calculate the load due to floor finish. We have given a load of 1 kilonewton per meter square. So multiplying it by 1 meter, that is the width of the slab, we get 1 kilonewton per meter. Live load is given as 3 kilonewton per meter square into per meter length, we get 3 kilonewton per meter as the live load. Finally, the dead load of each step is calculated by rise divided by 2 into density of concrete into 1 meter length of the waist slab. That is, we get 0.16 divided by 2 into 25 into 1. We get it as 2 kilonewton per meter. Therefore, the total load that we get is 4.6, that is this, plus live load due to floor finish, plus load due to live load, plus the dead load of the steps. So the total load W is equals to 10.6 kilonewton per meter, that is B to C. So next step is to the next step is to calculate the load for the landing slab. So it consists of self weight, that is depth of the slab into density 25 into per meter run, that is we get 3.875 kilonewton per meter. The second is the load due to floor finish, similarly that we have done in the previous step. Also there is live load that we have to consider, that is 3 kilonewton per meter. So the total load will be this plus the live load. We get 7.875 kilonewton per meter. This is represented as shown below. So this is 7.875 here, the UDL is shown, and 10.6 UDL is from the previous step. That is, this is the incline part and this is the landing part. So the landing length is 1.115, that is the landing width, plus bearing divided by 2. So we get 1.24 meter UDL from C to A. and from the previous step we have seen 10.6 kilonewton per meter. The length is 9 number of treads into tread of 0.25. We get 2.25 meter length. So the third step is to calculate the reactions RA, RB. So to do that, we choose the point A and we find the moment about it. So the summation of moment about point A is equals to RB minus RB into the whole length, that is 3.949, plus 7.875, that is this UDL. It is going in clockwise direction, that is 7.875 into 1.24 is the length into 1.24 by 2, that is 0.62, plus this UDL is also going clockwise with respect to point A, that is plus 10.6 into the length of the UDL 2.25 into the distance from point A, that is 1.24 plus 2.25 by 2, that is 2.365, and equating it to 0, we get RB is equals to 7.89 kilonewton. To find RA, we use the summation of forces in the vertical directions, that is RA is going upward is positive, plus 17.9 is RB which is going upwards, and 7.875 is negative UDL into the length 1.24. Also there is 10.6 kilonewton per meter UDL which is going downwards, and hence it is in negative, and the length is 2.25, and equating this to 0, we get RA is equals to 15.73 kilonewton. Consider a cross section at a length of x from B. So the summation of vertical forces we get at x, we get RB which is going upward is 17.89, negative is the UDL only this much, that is 10.6 into x, and equating this to 0, we get x as 1.69 meter. So we know that the moment is maximum at the point where the shear force is 0. Hence the moment we calculate at the point x, that is 1.69. So the moment at the point x is RB which is going anti-clockwise with respect to point x, that is 17.89 into x minus 10.6 which is going clockwise into the distance x into the center point, that is x by 2. We get the moment as 15.09 after substituting x as 1.69 meters in this formula. So mu, we know that the ultimate moment is 1.5 times the moment that we have calculated, that is 15.09 into 22.64 kilonewton meter. Coming to the step 4, that is the check for the depth. So we know that the formula for the required depth is square root of ultimate moment divided by 0.138 FCK into B. This is for FE 415. Okay, so the required depth is equal to square root of mu is 22.64 into 10 raised to 6. This we do to make the unit in Newton and mm, divided by 0.38 into FCK is given as 20, and this is calculated for per meter run. So the required depth we get as 90.57 mm, and the depth that we have provided is 135 mm, and the required depth that we have calculated is 90.57. Hence it is safe. The fifth step is to calculate the area of the reinforcement that we have to provide in the slab. So the AST formula we know is 0.5 FCK, that is 20, per meter run 1000 mm, and the depth is 135 mm, divided by Fy is given as 415, 1 minus root of 1 minus 4.6 mu we have calculated as 22.64 into 10 power 6 divided by FCK is given as 20, and B is per meter run 1000 mm into the depth squared, that is 135 squared. We get an AST of 503 mm square. So adopting 10 mm dia bars as the main reinforcement. So to calculate the spacing, we have the formula area of 1 bar divided by AST required into 1000. So the dia of 1 bar, that is 10 mm dia, pi by 4 into d squared divided by the AST required is 503.72 into 1000. We get it as 155.92 mm. So we provide 10 mm dia bars at a spacing of 150 mm center to center. Continuing, the AST provided is equals to pi by 4 into 10 squared by 150 into 1000. We get the AST that we have actually provided as 523.6 mm squared. AST that was required here was 502 mm squared, and the AST that we have provided is 523.6 mm squared. To calculate the AST minimum, we have the formula 0.12% of B into D. Calculating this, 0.12 by 100 into the depth is 155 total depth, and the B is for per meter run, that is 1000 mm. We get it as 186 mm squared. So the AST provided is 523 mm and the AST minimum is 186. So it is okay. So we have to bend alternate bars of the main reinforcement. So for the distribution reinforcement, we provide AST minimum, that is 186 mm squared. So adopting 8 mm dia bars for distribution reinforcement, we get the spacing as pi by 4 into 8 squared by the AST that we have to provide 186 into 1000, that is 270 mm. So providing 8 mm dia bars at 270 mm spacing. So the next step is check for shear. So considering the higher reaction value, that is RB 17.89 kilonewton as V, so we calculate the ultimate shear force, that is 1.5 into V, we get 26.835 kilonewton. So we know the formula for tau V, that is VU by BD. VU is 26.835 into 1000, that is kilonewton to newton, divided by B, that is 1000 into D, that is 135. So we get a value of 0.1988. So checking this value in table number 19 of IS 456, we can see for the given grade of M20, we have the least value of 0.28 and the value that we have got is 0.1988, which is lesser than 0.28. Hence the dimensions that are provided are safe. So the distribution shear reinforcement, that is we provide AST minimum, that is 186 mm square. We adopt 8 mm bars for distribution reinforcement, that is spacing is equals to pi by 4 into 8 squared divided by 186 into 1000. We get 270 mm. Spacing, we provide 8 mm dia bars at spacing of 270 mm center to center. So the last step is the check for deflection. So we calculate Fs, that is 0.58 Fy into AST required divided by AST provided. So it is, the Fy is given as 415 and the AST required is 503.72 and the AST that we have provided is 523.6. We get a Fs value of 231.56 Newton per mm squared. So the percentage of steel that we have provided is AST provided by B into D into 100. That is 523 is the AST provided into 100 divided by B value is 1000 into the D value, that is 135 mm. We get the percentage of steel that we have provided as 0.39%. So the distribution reinforcement permissible limit for deflection. So for this we use the figure number 4, that is page number 37 of IS 456 2000. So this is the figure. So the permissible limit is L by D is equals to 20 kT. So for this is the percentage steel reinforcement, that is 0.39. so 0.39 is somewhere over here. Okay, so modification factor we have to find out after we intersect with the line with the curves that are FS curves. So the FS curve, the FS that we have is 231. So the FS curve 240, we follow the curve 240, and 231 will be somewhere in line with 240. So intersecting 0.39% with FS curve of 240, we get a modification factor of 1.4. So 20 into 1.4, that is equals to 28. So we calculate L effective by D effective provided, that is 3.49 is the L effective divided by the effective depth that we have provided is 135 mm. So we get 25.9, which is lesser than 28. Hence the deflection is well within the permissible limit for deflection. Thank you.